Hello everyone. Welcome to Malaysia Online Tuition YouTube channel. In this video, we are going to be looking at A-Level Probability and Statistics 2 Confidence Interval Review Part 1. If you like and enjoy watching this video, then please give us a thumbs up. If you want to receive updates on our newest video, then please hit that subscribe button as well as the notification bell so that you won't miss any of our future videos. Alright, let's start with question number 1. Water is dispensed into 80 randomly chosen 1.5 liter bottles. The results X liters are summarized by summation of X equals 123.4 and summation of X squared equals 140.0. For part A, calculate the unbiased estimates of the population mean and variance of the water dispensed into the bottles. For part A, unbiased estimates of the population mean and variance, you can find the formula in MF19. It is provided, so you don't have to memorize. So for the unbiased estimates of the population mean, that is X bar equals summation of X divided by N. So summation of X is 123.4 and then N is 80. So just calculate 123.4 divided by 80. So we get 1.5425 liters. Okay, done. And then for the next part, which is the unbiased estimates of the population variance, which is S squared, the formula is 1 over N minus 1 and then open big bracket, summation of X squared minus and then summation of X over N. You square the value and then you close the big bracket. So replace everything. We have 1 over 79, open big bracket, 140.0 minus, open small bracket here, and then 123.4 divided by 80 and then squared, close the big bracket. So the unbiased estimates of the population variance, this one just now, 123.4 divided by 80, and then we square this, then 140 minus answer and then divide by 79. We get the unbiased estimates of the population variance to be 1.74 liters squared. Correct to 3 significant figures. And that's all for question number 1, part A. For part B, calculate a 90% confidence interval for the mean volume. For confidence interval question, first thing first, you have to start with the formula. So for the formula for confidence interval for the mean volume, or population mean, it is going to be CI. We have X bar and then plus minus. And then we have K times the unbiased estimates of the population standard deviation divided by square root N. So as you can see here, K depends on your confidence interval percentage. So in this case, for part B, we have the confidence interval to be of 90%. So how are we going to find the value of K? So we can write for 90% CI. Let me tell you first how to get this. So imagine you are sketching the bell-shaped curve. And then this is going to be your 90% in the middle. So since confidence interval is symmetrical, meaning that you have both tails to be having the same probability, so they are going to be 5% each. So altogether they are 100%. So now you can see that, let's say this is K. So you can see that the probability of Z less than K is 0.95. So to get a confidence interval of 90%, you are not going to be using 0.9 or the probability of 0.9. You are going to be using the probability of 0.95. So in MF19, under the normal distribution table, you have the table for critical value. So you are going to be taking the value of Z from there for the probability of 0.95. So let me check the value for a while. I cannot show the MF19. So the value of K is 1.645, according to the table. So now what we are going to do is we are going to use the formula, the X bar plus minus K times S over square root N. So for the lower value, it is going to be X bar, which is 1.5425, and then minus, K we already have 1.645 times, we have just now the unbiased estimates of the population variance, but we want the population standard deviation. So we have to square root both the S and the N together under 1 square root. So 1.74 divided by 80, like that, less than the population mean. And then we repeat the same thing, however this time we plus. 1.645 times square root of 1.74 over 80. Okay, so the final answer in three significant figures. So what we can do first, okay, this is the unbiased estimates of the population variance just now. We divide by 80, okay, and then we square root this, and then times 1.645. So what are we finding right now actually is called the bit, okay? So why do I call it the bit? Okay, because this one, if you realize, right, 1.5425 minus a little bit, 1.5425 plus a little bit. So that's why we call this part bit. Okay, so just now we found the bit already. So we store this bit inside the letter A, for example, and then we can write 1.5425 minus a little bit. So we get 1.30 for the lower value. And then for the upper value, we plus. We get 1.79. Okay. So this is the final answer for question number 1, part B. Finally, for part C, estimate the smallest random sample required for a 95% confidence interval to have a width of at most 0.05 liters. Okay, so now you can see that we are using a different confidence interval, which is 95%. So we need to find a new value of K. All right, so again, the same formula as in part B. So we are going to write, oh yeah, by the way, before that, okay, we can see the bit, right? So you have to know what is the relation between width and bit. So width is actually twice the bit, okay? So that means since we want the width to be at most meaning maximum, right? So width is less than or equals to 0.05. So for bit is going to be less than or equals to 0.05 divided by 2. So we want our bit to be less than or equals to 0.025, okay? So we already know what is the formula for bit, okay? I've shown you already in part B. So we have K times S over square root N less than or equals to 0.025. So for the value of K, we have to find a new one because we are using a 95% confidence interval. And later we can find the value of N, which is what we want. So now for 95% CI, probability of, okay, the same method, okay, I don't have to sketch a new diagram and all. You can determine this on your own. I will just give you the answer straight away. Probability of Z less than K equals 0.975. So the value of K is going to be, okay, let me pause for a while. I don't want to show the MF19. For probability of 0.975, the value of K is 1.96, okay? So now we can substitute that inside the formula. So 1.96 times, okay, this one is going to be square root of 1.74 divided by N, okay, because we want to find the N, less than or equals to 0.025, okay. So now we can shift one by one. So square root of 1.74 over N less than or equals to, so 0.025 divided by 1.96, we get 5 over 392. And then we square this, okay? So 1.74 over N less than or equals to. So we square this, we get, okay, because when we shift the square root, the other side is going to be squared. So we get, oh, that's a very small value. 25 over 153,664. Okay, 25, right? Okay, 25. So finally, the value of N is going to be greater than or equals to, as you can see. So this value, right? Okay, 1.74 divided by that value. So we get 10,695.0144. Okay, 10,695.0144. So in this case, since you want the smallest random sample, so this must be integer. Okay, remember, because the number of water bottles must be integer, right? You cannot have, for example, 1.3 bottles, right? So it must be an integer. So the next integer that comes after 10,695 is going to be 10,696. So smallest N is going to be 10,696. And this is your final answer for question number 1, part C. Next, for question number 2, a random variable x is normally distributed, with x to be normally distributed with mean mu and variance sigma squared. Based on a random sample of 50 observations, the 99% confidence interval for mu is given by 14.0 until 15.2. Find for part A the value of sigma. Okay, so for this question, right, you have to use the information given, which is the confidence interval. Okay, so as usual, since they give us 99% confidence interval, you have to know how to find the value of k. So for 99% CI, okay, our value of k, okay, probability of z less than k is going to be 0.995. Okay, so I want to find for a while what is the value of z when our probability is 0.995. So the value of k is going to be 2.576, okay, for 99% confidence interval. Okay, so next, how to use the confidence interval given, which is from 14.0 until 15.2. So when you subtract, when we subtract 15.2 and 14.0, that is width, okay, meaning when you subtract the upper and lower value, that is the width. So then our width is going to be 15.2 minus 14.0, and that is going to be 1.2. So this is the width. And remember, the relation between width and bit is going to be bit is half of the width. And then we know the formula for bit, and that is going to be k times s over square root n. Okay, something like this. So then that is going to be 0.6. So we know the value of k. So our k is 2.576. Then what we are looking for right now is the sigma, right? So we can just replace that with sigma and then divide by square root n. That is going to be square root 50 equals 0.6. So then our sigma is going to be, oh my god, that is a hideous one. Our sigma is going to be, so 0.6 divide by 2.576 times square root 50. So we get the value of sigma to be 1.65. Correct to 3 significant figures. And that's all for question number 2, part A. For part B, the size of random sample that will give a 90% confidence interval for mu of width as close as possible to 0.6. Okay, so be careful of this. Width as close as possible to 0.6. So what are we going to do first? As usual, you check the confidence interval. It is a 90%. So we need to find the value of k. So for 90% CI, probability of z less than k equals 0.95. So for 0.95, the value of k is 1.645. Okay, wait, let me check. Okay, the value of k is 1.645. So when they say the width to be as close as possible to 0.6, then we just write width equals 0.6. Okay, this is not an inequalities. This is just equation. Okay, we just want to see what is the random sample that will give us the width as close as possible to 0.6. So width done. So bit is going to be half of the width. So we can replace the formula for bit, and then our k is 1.645 times. Then our sigma, okay, is 1.65, correct to 3 significant figures, divide by square root n equals 0.3. So now we need to find what is our value of n. So we find first what is our square root n. So this value just now, okay, so 0.3 divide by the answer, divide by 1.645. Okay, so we get this. So wait, shift there. Oh, we have to turn upside down. Okay, so 1 divided by this, we get 9.031, something like this. Okay, and when we shift the square root to the right hand side, it is going to be squared. So when we square this, you will get 81.56. Okay, so since our n must be an integer, so then the closest value, because you can see, right, you can choose between 81 or 82. But since 81.56 is closer to 82 rather than 81, that's why the answer that will give you the width as close as possible to 0.6 to be n equals 82. Okay, so that's how you get the answer for this question number 2, part B. Now for question number 3, rolls of tissue paper of a particular brand are claimed by the manufacturer to give on average at least 20 meters of tissue paper. The manufacturer receives some complaints about the actual lengths received by customers, so the quality control manager takes a random sample of 50 rolls and measures the length x meters of each roll of tissue paper. The results are summarized by summation of x equals 1098.25 and summation of x squared equals 23,184.48. For part A, calculate a symmetric 99% confidence interval for the population mean length of tissue paper for this brand. For part A, start with the 99% confidence interval first. So for 99% CI, okay, as usual, probability of Z less than K to be equal to 0.995. Okay, so we need to get the value of K first. So for probability of 0.995, the value of K is 2.576. Okay, so now we can start with the formula. So before that, we need to find the, before we use the formula to find the confidence interval, we need the unbiased estimates of the population mean and variance. Okay, so x bar equals summation of x over n. So 1098.25 divided by 50. So what is it? 1098.25 divided by 50, we get 21.965 meters. Okay. And then for the unbiased estimates of the population variance, S squared. Okay. So this is going to be 1 over n minus 1. Okay. So we just write 1 over 49, open bracket, open big bracket, 23,184.48 minus, open small bracket, 1098.25 over 50, and then we square this value and then we close the big bracket. So the unbiased estimates of the population variance, okay, this is the one just now, we square this, and then 23,184.48 minus answer, and then we divide everything by 49, we get 463.31, okay, square meters. Okay, this is the unbiased estimates of the population variance. So now we can use the formula. So x bar, which is 21.965, minus our value of K is 2.576, times the, so since we want S, right, we want the unbiased estimates of the population standard deviation. So we put the square root, and then for the 463.31 over 50, okay, less than the population mean, less than, we repeat everything, plus 2.576 times square root of 463.31 over 50. Okay, so that is the bit, right? So then we can first calculate the bit. So the bit is going to be 2.576 times square root of 463.31 over 50. So we can save this inside our letter A, for example. So 21.965 and then minus A, we get 14.1 meters. And then plus A, we get 29.8 meters. Okay, so this is the confidence interval, 99% confidence interval for the population mean length of the tissue paper for this brand. Okay, so that's all for question number 3, part A. So now for part B, are the complaints justified based on the confidence interval obtained in part A? Give a reason for your answer. So this one is clear cut, okay, the answer. Complaints justified, okay, since why? You can see that the population mean can be as low as 14.1. So if the manufacturer advertised that this roll, the rolls of tissue paper sold, okay, by them, have to have at least 20 meters of tissue paper, but now the confidence interval, right, based on the confidence interval, it can be as low as 14.1. So the complaints are justified because it can be as low as 14.1, meaning anything less than 20, okay, the complaints are justified. Okay, so we can say complaints justified since mu can be less than 20 meters. You can just say like that, okay, can be less than 20 meters, or you can say can be as low as 14.1 meters. Imagine you bought something that they advertise to be having at least 20 meters, but then you get only 14.1. Of course, you are going to be unsatisfied, right? So yes, the complaints are justified, okay? Can be as low as 14.1 meters based on the confidence interval, right? So of course, like if you get a little bit more, then yeah, it's a bonus. But if you get less, that's the problem, okay? So then this is how you justify for part B here, okay? So that's all for question number 3. Moving on to question number 4, a random sample of 100 bananas having a mean mass of 180 grams and unbiased variance of 150 grams squared are investigated. For part A, find a 98% confidence interval for mu. For part A, they gave the mean mass of 180 grams already, so that is x bar equals 180 grams. And the unbiased variance, meaning that it's going to be the s squared, equals 150 grams squared. Okay, so everything has been given, so you just have to find the value of k now. So for 98% CI, then we can write probability of z less than k to be 0.99. So then the value of k according to MF19, okay, this is going to be 2.326. Okay, let me check for a while. Okay, so yes, it is 2.326. So then we can apply the formula straight away. So what's the formula? X bar, which is 180, minus the value of k, which is 2.326, times the s over square root n. So since you have s squared here, so we can put the s squared and the n straight away under 1 square root. So 150 over our n is 100. Okay, less than the population mean, and the less than 180 plus 2.326 times square root of 150 over 100. Okay, so for the final answer for the unbiased, for the 98% confidence interval, so we find the bit first. So 2.326 times square root of 150 divided by 100, that is 1.5. So times square root 1.5. So we get this. So we store this inside the letter A, for example. So 180 minus A, we get 177, correct to 3 significant figures. And then for the upper value, we get 183. So this is the final answer for question number 4, part A. For part B, given that the width is 10.2 grams for a confidence interval of alpha %, find alpha. Okay, this one, they give us the width, but they didn't give us that this width is obtained from what percentage of confidence interval. So as usual, we start with the width, which is 10.2 grams, and then you know that we have to find the bit, because we know what's the formula for the bit, right? So 10.2 divided by 2. So the bit is k times square root of 150 over 100 equals to 5.1. Okay, so now our mission is to find the value of k. So then according to this, the value of k is 5.1 divided by square root 1.5. We get 4.164. Okay, this is too big, okay? So something wrong here. Okay, wait, I think I have to change my width, because this question I made it on my own. So I think this value is too big, okay? So I have to change it for a while. Okay, let's try to use a width of 5.0 grams, okay? And then see whether we get an acceptable answer or not. So let's say the width is 5.0. So the bit is 5.0 divided by 2. So this is 2.5. And then let's recalculate, okay, the value of k. So now our k is 2.5 divided by square root of 1.5. So we get the k to be 2.041. Okay, that is better actually. 2.041. So this is something that we can have from the table, from the normal distribution table, okay? So now the method on how we can get the alpha % confidence interval. So you imagine you sketch the bell-shaped graph, okay? Remember the k here is the value of z, okay? So k is 2.041, so you can say here is 2.041. And then of course you must have another one which is negative 2.041 over here. So in the middle here is your alpha %, okay? So we don't know yet what is this, okay? So now what we need to find is we need to find the red color. Okay, so now what I can say is probability of z greater than 2.041 is equal to, okay, wait, is equal to 1 minus probability of z less than or equals to 2.041. So we need to find what is the probability of z less than 2.041. So the probability is 0.9793. So 1 minus this, what do we get? So 1 minus 0.9793, so we get 0.0207. Okay, or in percentage, this is going to be 2.07%. Okay, so since the red color is 2.07, so we have two of them, so we have to multiply by 2. So then how to get alpha is very simple. You know that the total is 100%. 100% minus the two red colored regions. So that is going to be 2 times 2.07%. This is how you get the value of alpha percent confidence interval. So 2 times 2.07 and then 100 minus answer. So we get correct to 3 significant figures, okay, or maybe to the nearest integer lah, okay, 96% confidence interval, okay. So this is the final answer for question number 4, part B. Finally, we have reached the final question of this video, which is question number 5. A biased die was thrown 500 times and among those were 212 fives obtained. For part A, given that P is the probability of obtaining a 5 when the die is thrown, find a 95% confidence interval for the population proportion P. Okay, so now for part A, we know that we have the die to be thrown 500 times, so the sample proportion is going to be 212, okay, number of 5s obtained, divided by 500. Okay, so we can just leave it like this. Okay, if you want to find the decimal value, that is 0.424. So as usual, 95% confidence interval. So for 95% CI, okay, you are going to be doing this every single question, okay, if they ask for it. So probability of Z less than K equals 0.975. So this value of K is going to be 1.96. Okay, done. So for the formula for population proportion, okay, so we can write first, because all this while we have been doing in this video, population mean, right? So this is the first question that we have seen, population proportion. So the formula is going to be P bar, okay, or the sample proportion, plus minus K, and then square root P bar times 1 minus P bar over N. Okay, this is the formula. So now we can apply this. So sample proportion, which is 0.424, minus the K, which is 1.96, times square root of 0.424 times, okay, so 1 minus 0.424. That is 0.576. Divide by N, okay, which is 500. Okay, and then we do less than the population proportion, and then less than, we repeat everything. Plus 1.96 times everything again. 424 times 0.576 over 500. Okay, as usual, we find the bit, okay? We find the bit first. So square root of 0.424 times 0.576. Actually, I have to do this straight away. 0.424 times 0.576 divided by 500 and then times 1.96. So this is the bit. So we store this inside A. So 0.424 minus A. What do we get? 0.381 for the lower value, and then less than the population proportion, and then the last one, we plus A, we get 0.467. Okay, correct to 3 significant figures for the final answer. So this is the final answer for question number 5, part A. For part B, given that the width of a 95% confidence interval for P is to be at most 0.1, estimate the least number of times the die should be thrown. Okay, so this one, the least number of times the die should be thrown, this is the value of N. Okay, so we are looking for the value of N now. Okay, so remember they said the width at most 0.1. Okay, so remember width and then bit. So start with width. Width must be at most, meaning maximum is 0.1. So we can write less than or equals to 0.1. So then the bit is less than or equals to 0.1 divided by 2. So the bit, remember, the formula is for population proportion, not the population mean. Okay, we have been doing the population mean formula. So remember that this is proportion, use the proportion formula. So we have the K, 95% again, so you don't have to find a new one. 1.96, and then times the square root of 0.424 times 0.576 divided by your N, the one that you are looking for. less than or equals to 0.05. Okay, so let's do this slowly. Okay, so square root of what? So we know that 0.05 divided by 1.96, we get 5 over 196. And then 0.424 times 0.576, we get, oh, that's quite long, 0.244224 divided by n. So now we are going to shift the square root to the right hand side, meaning that it's going to be squared. So 5 over 196, and then we square this, we get 25 over 38416. And then on the left, we have 0.244224 over n. And finally, our n must be greater than or equals to, so remember that value, we shift to the left, it's going to be divided. 0.244224 divided by answer, we get 375.28. So since we want an integer, because you know that the number of times the die should be thrown will be an integer, right? So something must be more than 375.28. So the next integer is going to be 376. So least number of throws, okay, so that your width is at most 0.1, is going to be 376. Remember to give an integer answer, okay? So that's all for question number 5, part B, and that's all for this video, confidence interval review part 1. So if you have any question or any comment, please leave them in the comment section below. So if you like and enjoyed watching this video, then please give us a thumbs up. If you want to receive updates on our newest video, then please hit that subscribe button as well as the notification bell so that you won't miss any of our future videos. Thank you very much for watching this video, and finally, please take care, and I hope to see you in our future videos.